All right, let's look at some hints for homework 7. Problem 1, we're looking at a system of linear equations. And so the idea is you've got a coefficient matrix A, and we want to find matrices P and Q that diagonalize that system. So diagonal. And then you make a change of variables where you're going to let y be, or rather x is going to be q times y. So then when you put a y here, you'll get a very simple diagonal system, and the new variable is y. Okay, so A is the coefficient matrix, so let's write that down. 1, 1, 4, 2. And you'll have 5, and then -3, -1, 0, -6, 3. -1, -1, 2, -2, 1. And then you don't need to keep track of the row operations. So P is doing the row stuff, Q is doing the column operations. And so I just want to keep track of the column operations, so I augment this matrix with an identity matrix. Quiet, Smokey. 0, 0, 0, 0, 1. Okay, so our first step is to clean up these 3 entries by doing appropriate column operations. So I'm going to do minus column 1 added to column 2, minus 4 times column 1 added to column 3, and minus 2 times column 1 added to column 4. Okay, so just do that. I'll just give you an example of one of those operations. So I'll leave the first column completely alone, and minus the first column added to the second column, 3 added to -1, -1 times -1 added to -1 is 0, -1 added to 0, 1, 0, 0. And then you do the same thing to all of this stuff, and you get a 0, 0, 0 with some numbers down here. And we're just doing column operations so far, so I haven't changed the 5, 3, and 1. Okay, and then after you've cleaned up these 3 entries, step 2 is you want to clean up those 2 numbers by doing appropriate row operations. So I would take like 3 times row 1 added to row 2, and 1 times row 1 added to row 3, and that's going to create zeros in these 2 positions. Then you come and focus your attention on this part of the matrix, and you continue diagonalizing that part. So at the end, in the lower left corner, so etc., etc., you go through some more steps. In the lower left corner is the change of variables matrix Q, and so you just set x1, x4 equal to Q times y1, y4, and you'll have your diagonalized system up here. You'll have some diagonal entry d1, y1 equals a b1, and a d2, y2 equals b2, etc. And you just go ahead and solve the system. So you can read a complete worked out example in the notes there. Number 2, for what integers a and b can we solve the following system in integers? So again, just set it up. This. And we want to keep track of the column operations again, so I augment it with the identity matrix right here, and do the row operations. So the first thing I want to do is move the 1 into the upper left corner. So I would suggest doing column 1, column 2 swapping, or row 1, row 2 swapping, just to get yourself started. You could move this -1 over here as well. So either way would work fine. Okay. And then once you have that, go through and diagonalize your matrix. So once again, you're going to eliminate these 2 entries to get some zeros here, and then you're going to eliminate this entry to get a 0 here, and you'll have some combinations. You want to keep track of the B and A's as you're doing those different row operations, and in the end you'll have your come down and find your Q matrix, and you'll have a diagonalized system. D1 Y1 equals some B1 entry, and a D2 Y2 will equal some B2 entry, and you'll discover, aha, this is solvable if and only if D1 divides B1 and D2 divides B2. And so that'll give you some constraint on what B and A have to be in order to be solvable, and then you actually solve the system by introducing the change of variables matrix. So again, I have a example worked out in the notes you can take a look at. Number 3, find all rational points on the ellipse starting from this point right here. So we have some ellipse that passes through -1, 0, obviously. And when x is 0, you're passing through some other points here. So some type of ellipse like that. Okay, and so we're just going to use the method of chords. So I'm going to draw a straight line like that. So the equation would be y equals the slope times x plus 1. And then we find the point of intersection. So intersect, call this line LM, and find LM intersect the ellipse. So we just plug in this into the equation, x squared plus 5 m squared x plus 1 squared equals 1. And then a little trick for solving this. Is rather than multiply it all out, put it into a factored form on the right hand side, so you can see this factor of x plus 1 canceling, and solve for x. Okay, so that'll give you the second point of intersection, and then you let the slope m run through the rationals to find all rational points. Okay, and then here we're just continuing. So once you've solved problem 3, we can find all integer points. After all, if you have an integer solution of this equation here, this would say that x over z squared plus 5 y over z squared equals 1. So x over z, y over z is a rational point on the curve we just looked at in problem 3. Okay, so I've split it into 2 parts. So first of all, I'm going to show you what the solution set looks like. So let x be any number of this type, blah, 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 blah. Show that this is a primitive solution. To show that it's a solution is just inserting it into star and grinding it out. No problem there. And then to show that it's primitive means we look at the GCD of any two of these things. So suppose you're looking at the GCD of s squared minus 5r squared in 2rs. And just asking, okay, is there anything that these two numbers can have in common, given the fact that r and s are relatively prime? Well, since r and s are relatively prime, you can break that into different categories. Let's see, what do we know about even and oddness? So s and r are not congruent mod 2. So one is even and one is odd. And yeah, they can't both be even because that would violate this. So exactly one is even and one is odd. So what does that mean? S squared minus 5r squared is even or odd? So if s is even, this is 0, and r is odd, this would be an odd number. And if s is odd, this is 1, and this is 0. So this seems to be an odd number. So the 2 is not going to play any role. And then r and s are relatively prime, so you can kind of break that up like this, etc. Okay, so calculate these GCDs just using basic properties. Subtract a multiple of s from s squared, etc., etc. And then use the preceding problem to show that every primitive solution is of this form. Well, okay, so you need to have a solution. Let's see, did I work that out? You get some solution. So maybe I have something like x. You'll have to check my calculation here. So that's what a typical rational solution looks like that I got from the preceding problem. And then m you can write as some fraction. So m is some a over b, with ab relatively prime. And so you can reduce this expressed in terms of a and b. And show that the expression you get after some time is a reduced fraction. So after you insert this in for m and simplify these expressions, you want to show that you get something in reduced form. And the way we know that it's reduced is by the very same type of thing you did in part A. You'll get these type of things, and you just need to show they're pairwise relatively prime. Okay, so it's very similar to what we did for Pythagorean triples, so just play with it like that. Describe all triangles having a 60-degree angle and all sides of integral lengths. Okay, so they don't have to be right triangles, they just need a 60-degree angle here. X, Y, and Z. And okay, so what type of equation do we get here? We have the law of cosines. So z squared is x squared plus y squared minus 2xy cosine of 60 degrees. Okay, so that's the equation we're looking at. And so proceed like we did in the previous two problems. Find the rational points. So I'm going to divide through by z squared. Like this. And so step one is we want to find the rational points on the curve 1 equals x squared plus y squared minus xy. So step one, and then after we find those rational points, we'll put in and proceed like we did in the previous problem. Okay, so what are some rational points on this curve right here? You want to, hopefully there's a very easy one to identify, such as 1, 0, or how about our favorite one, which is when y is 0, x is negative 1. Yeah, when y is 0 and x is negative 1, that's certainly a point on the curve, right? Y is 0, x is negative 1. So then we draw a line through that point, intersect it with a curve, etc. And find the second point of intersection, and then let m equal a over b, with the GCD of a and b relatively prime. Okay, and then come back, after you get those rational points, we come back up here to find out what the integers x, y, and z are. And I think when I did this, there were two categories of points that you need to think about. One is where a is congruent to 2b mod 3, and a second type is when a is not congruent to 2b mod 3. Yeah, because the GCD doesn't have to be 1. You're going to have some GCD condition that comes down to something like this, which could be 1 or 3, depending on which of these two cases we're in. And so you'll start off looking like you have two different families of solutions, and then you kind of put them together. All right, this one looks an awful lot like Fermat's last theorem, x to the n plus y to the n is z to the n, which of course we know has no solutions once n is at least 3. But I claim here we have infinitely many if we just add on one more to the z power. And the catch here is I'm not insisting that these be primitive. So we're just trying to find some easy solutions. Find some non-primitive solutions. That hint alone may help you do it. So you may not want to proceed to hear what I'm going to say next. Try this. Y equals, yeah, try them all to be a multiple of x. Try something like that. say y is lambda times x, and z is beta times x, where lambda and beta are some integers. And see if you can find solutions where y and z are some multiples of x. Okay, show that this has infinitely many primitive integer solutions. Well, you can immediately see that any solution to that gives us a Pythagorean triple. So we want to find a special type of Pythagorean triple. And we know that Pythagorean triples are of this form. X is going to be u squared minus v squared. Y is going to be 2uv. And z squared is going to be a u squared plus v squared, where u and v are relatively prime, and one is even, one is odd, and one is bigger, and one is smaller, etc., etc. So we're trying to find solutions, and the one thing that we want to focus on is right here. But that is itself a Pythagorean triple. So these u and v's are free variables, and we want to find u's and v's that would satisfy this third equation. So they're part of a Pythagorean triple. Well, that would say I want little u to be a capital U squared minus a capital V squared. I'd want little v to be a 2 capital U capital V. And I'd want z to be a capital U squared plus a capital V squared. And now the capital U and capital V are these free variables that are pairwise relatively prime. One is even, one is odd, etc., etc. And so if I choose my capital U and capital V of that type, and I define little u's and little v's and x, y's, and z's in this manner, it looks like I'm going to end up with a solution to start. Okay, so try that out. Number 8. Use the method of descent to show that these equations have no solutions. So we just slightly modify this one. So this one works because we have 2 quadratic terms in 1/4 power. But in all of these equations that have 2 4th powers and 1 quadratic, or have all 3 to have 4th powers, there tends to be no solutions other than the trivial ones. So again, how do we get ourselves started? We want to show that, let's call this 1 and this 2, that given a solution of 1, we obtain solution of 2 with a smaller z value, and vice versa. Given a solution of 2, we can obtain a solution of 1. And so each time we proceed, we're going to get a smaller and smaller z coordinate, and therefore we're going to have a contradiction. You can't proceed to find solutions with z getting smaller and smaller, but staying positive. So how do we get to first base then? So suppose x, y, z satisfies 1. Well, that looks an awful lot like a Pythagorean triple, because that would say x squared squared plus 2y squared squared is z squared. So that implies that x squared is some u squared minus v squared, that 2y squared is a 2uv, and that z squared is of this form, for some uv relatively prime, with u even and v odd. So this cancels out here. And then since u and v are relatively prime, this equation is going to tell us that u is a perfect square and that v is a perfect square. Okay, and then once you know that those are perfect squares, how do we get a solution to 2? So one of these equations is going to give us a solution to 2. So you figure that out. And then part 2, given a solution of 2, we need a solution of 1. So you say suppose x, y, z satisfies 2. Well, this time we have, once again, a Pythagorean triple. And so x squared is this, y is 2uv, and z squared is a u squared plus v squared. And so you should be able to proceed to obtain a solution of 1. And that will do the trick. Okay, now this problem really depends on that previous problem. So find all rational points on the elliptic curve y squared is x cubed minus x. Well, there are some easy to identify points. When x is 1 and y is 0, that works. And of course this is an odd expression, so when x is negative 1 and y is 0, that would also work. And let's see, if x is 0, what solution do we get? Well, 0, 0, so these are easy to spot. Okay, now let's try using our chords and tangents or something to try to create some more points. So let's take our favorite one and draw the line y equals m times x plus 1, where m is a rational number. Okay, and then intersect with the elliptic curve. So we would have m squared x plus 1 squared is x cubed minus x. And then keep in mind that one of the points of intersection is negative 1. So you know that x plus 1 is a factor. And so try to, without multiplying things out, to kill that factor. And that will allow you to come down. Now this time you're not going to get a linear equation where you can say x is some rational number. You're going to end up with a quadratic equation. You're going to have something of the form x squared plus ax plus b equals 0. And there will be the m involved. Now, what have we done here? You've taken your elliptic curve, zoom, something like that, oops, like this. We've drawn the line through negative 1 here, boom, 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 and it intersects at 2 points. And we want both of those points to have rational coordinates. That means we want rational zeros, 2 rational zeros. And every rational point on the curve will be of this type, because if we started with one of these 2 points being rational and I drew a line of slope m connecting those points, it would have a rational slope. So how do I know when a quadratic has rational solutions? Well, you need the discriminant to be a perfect square. Well, what's the discriminant? That's like I should have called this b and c. It's a squared minus 4b in this case. Needs to be some perfect square, like that. And so you end up with another Diophantine equation. Now, you're going to start off with this having some rational numbers, but then you can transform it so that b squared minus 4ac. Yeah, you're going to have to actually see what it looks like with the m involved. But you want to transform it into an equation with just integers. So your m is going to be some rational slope, and you call that some a over b or r over s, whatever. You're not going to have these letters a and b in your calculation. So you transform this into an integer equation. And out should pop up one of these 2 types of equations that needs to be solved in order for that discriminant to be a perfect square. But these have no solutions in positive integers. That's going to tell you that there aren't a whole lot of rational points on this curve. And there's going to be something very special about this set of points, because one of the coordinates is equal to 0. Over here, we were insisting that these were solutions with all positive integers. So when one of the coordinates is 0, we call those trivial solutions. So, I've said enough, I think. And then number 10, show that the projective curve is non-singular. We just have to calculate all of the partial derivatives. And so that's just grinding out some partial derivatives. Is there anything special there that would come to mind? I don't think so. Show that the projective curve defined by this homogenized polynomial f of x, y, z is this. So it might be useful to actually write out what f of x, y, z looks like. So z cubed times f of x over z, y over z. And then x over z, you're just plugging that in for x. That. Okay, the z cubed is sitting out here like that. Okay, so that's gonna, I can't read my green. Looks like a z y squared minus x cubed plus ax squared z. So we're just homogenizing the polynomial here. So cube like that. Okay, so that's what f of x, y, z looks like. And now you need to calculate the partial derivatives. And the question is, well, do you want to use this form or use the original form here? And you can do it either way. So partial f, partial x would equal partial x of z cubed f of x over z, y over z. So if I do it in that form, z is treated like a constant, and then we use the chain rule, so I have to take partial f, partial x, evaluated at this point right here, times the derivative of the first coordinate with respect to x, and that looks like 1 over z. Okay, so that's that. And you're going to want to set that equal to 0. And then you do partial f, partial y, and you'll set that equal to 0. So what does it come out to be? Probably the same thing. Okay. And then you'll have partial f, partial z. What's partial f, partial z here? Yeah, well, you could use the product rule on that, or do we just want to come back to this one right here? And you remember, we're going to be at a point on the curve. So if I want to use the product rule, you take the first one times the derivative of this with respect to z. Okay, so partial f, partial x, and then what's partial z of this? That's z to the negative 1, so minus x over z squared. Kind of looks weird. Let's see what's going to happen here. And then we're doing product rule, so plus 3z squared f x over z, y over z. And these things are all being evaluated at the appropriate places. So, well, okay. When you're putting all this together, you'll get certain points where either z is 0 or these partial derivatives are both 0. So if z doesn't equal 0, what do you conclude? Just from the first two equations. And we are given that this is an elliptic curve. So that means what? That there were no singularities, there were no places on the curve where both of these partial derivatives vanished. Okay, so in that case we're done. There would be no solution where both of these are equal to 0. And so you're just left with a case where z is equal to 0. And when z equals 0, what points are on the elliptic curve? Well, there aren't a whole lot of points. You just have the one point at infinity on the elliptic curve. And you just show that that's a non-singular point. Okay, well, anyhow, there's probably just as straightforward to go back to the original equation and not monkey with all of this business. Stop that.